On July 12, 2022, NASA announced the first images from the James Webb Space Telescope, revealing a shock. Scientists were very surprised by the discovery of fully formed, massive galaxies like the Milky Way. More than 13 billion light-years away from us, containing hundreds of billions of stars. They are believed to have existed when the universe was still young, completely unlike a young universe, as the Big Bang Theory once claimed. In addition, James Webb also discovered supermassive black holes. This led to a bold hypothesis that primordial black holes were born directly from the first gas clouds of the universe. They may even have appeared right after the Big Bang. Have we misunderstood time, space, and the origin of the universe? Or does the universe operate according to laws that have never been written? Are you ready? And right now we will enter the things that have never been written in the history of the universe. A place that may change every thought you once had about it. After the initial shock delivered by the James Webb Space Telescope, what truly puzzled the scientific community wasn't just the early appearance of galaxies, but the nature of those galaxies themselves. These were not scattered clumps of stars, but well-structured giants with dense cores, each containing hundreds of billions of stars. Galaxies like Sears 93,316 and Glass Z13 appeared with masses equal to or even exceeding that of our present-day Milky Way. Why does this matter? Because according to the standard lambda cold dark matter model, galaxies require immense time to evolve. The formation process begins with primordial hydrogen clouds. Then the first stars ignite, followed by supernovae creating heavier elements, which later reassemble into new star systems, a cycle believed to take billions of years. And yet, James Webb is capturing what seems to be that entire process compressed into just a few 100 million years. This isn't a measurement error nor a statistical fluke. Independent observations all point to a consistent truth. Mature galaxies appearing in unison during what should have been the universe's infancy. Even more compelling, the light spectra from these ancient galaxies reveal the presence of heavy elements like oxygen and iron. Materials that require multiple stellar life cycles to produce. This means not only did these galaxies form rapidly, but they also aged at an accelerated pace, far beyond the limits of our current understanding of physics. And we can't ignore the disconnect. The universe's largest and most advanced simulations, Illustris, DNG, Eagle, Simba have failed to reproduce such massive early galaxies. These models predict a slower cosmic evolution, consistent with Big Bang logic. Yet the data from James Webb tells a different story, one that contradicts this logic entirely. Could the universe be hiding an unwritten chapter? If time isn't absolute, are we perhaps gazing at a compressed present shaped by a very different past? The presence of massive galaxies like Sears 93,316 or Glass D13, only a few hundred million years after the Big Bang, does more than challenge the timing of cosmic structure formation. It raises a deeper, more profound issue. The universe's rate of evolution may be calling into question the entire timeline of cosmology we rely on. According to the standard lambda-cold dark matter model, the emergence of matter after the Big Bang follows a relatively well-defined sequence. Around 380,000 years after the explosion, the universe cooled enough for protons and electrons to combine into atoms, a moment still imprinted in the cosmic microwave background. Only after 100 to 200 million more years did the first stars ignite, and protogalaxies began to coalesce roughly 500 million years after the Big Bang. This is the foundational timeline upon which all modern cosmological models are built. Yet James Webb is now observing mature galaxies clearly structured and packed with hundreds of billions of stars, already existing just 300 to 400 million years post-Big Bang. That means these galaxies would have had to move through all key evolutionary stages. First-generation star formation, stellar clustering, multiple stellar life cycles for heavy element recycling, and full galactic stabilization in less than half the time current theory deems necessary just to begin the process. Has the universe somehow accelerated beyond the limits of known physics? Or are we simply measuring time incorrectly? One hypothesis gaining traction among physicists is that time itself may not be absolute, but rather shaped by the extreme physical conditions of the early universe. According to Einstein's theory of general relativity, time and space are interwoven into a single fabric. In regions of extraordinarily high energy density and gravitational fields, such as during the universe's infancy, time can dilate, compress, or slow down. If this time distortion occurred on a cosmic scale, then events like galaxy formation and element synthesis could have unfolded far faster than they appear from our current frame of reference. Some theoretical physicists have proposed that time might not only flow faster or slower, but could fragment or even cease to exist as a continuous entity. In models of quantum gravity or higher dimensional universes, time may not be fundamental at all. Instead, it could be an emergent property, rising from deeper, hidden relationships between particles and energy. If true, the timeline we use to calculate the age of the universe may be nothing more than a blurry projection of a far more complex reality. So is the time we're measuring even real? Or are we merely tracking a surface-level illusion, while the true depth of time lies buried beneath layers of cosmic structure we've yet to perceive? James Webb isn't just measuring distances or brightness, it's brushing up against the very fabric of time itself. a current that physics and philosophy alike have yet to fully comprehend. And if those distant galaxies truly are older than time allows, then perhaps the ruler we've been using to chart the universe needs to be recalibrated from the ground up. If the data from James Webb suggests that time could be distorted or compressed in the early universe, could it mean that our current cosmological model is simply incapable of replicating what truly happened? Today, three opposing theoretical directions are being weighed, each a bold attempt to explain observations that no longer fit within the boundaries of our standard models. The first approach focuses on refining the model of galaxy formation. Some hypotheses propose that in the early universe, the density of dark matter, the invisible substance that accounts for 85% of all mass, may have been far higher than previously estimated. This increased density could have generated immense gravitational pull, accelerating the collapse of matter, igniting star formation, and allowing galaxies to form much faster than expected. In this scenario, the first supernova explosions may have occurred at dramatically higher rates, suggesting a wildly turbulent newborn universe where star formation raced at hundreds of times the pace we see today. But simulations reject this idea. Large-scale programs like Illustris.ng, Eagle, and Simba, which integrate millions of variables, have never produced galaxies that are both this early and this tightly structured, as seen by James Webb. The gap between theoretical models and observable reality is only growing wider. The second approach considers potential errors in astronomical observation itself. Some ancient galaxies may contain hyperluminous black holes at their centers, making the entire structure appear brighter and older than it actually is. Additionally, gravitational lensing, when light is bent and magnified by intervening matter between the galaxy and the telescope, can also distort images and amplify brightness. However, these phenomena cannot account for all of the galaxies James Webb has captured. Many are too distant, too uniformly aligned, and show no signs of distortion, ruling out lensing or deceptive cores as blanket explanations. The third hypothesis is the most radical. A complete revision of our cosmic model. A few physicists are revisiting the once dismissed tired light theory, in which light gradually loses energy over time, and redshift is not solely a product of universal expansion. Based on this framework, new estimates suggest that the true age of the universe might not be just over 13 billion years, but could extend to 26.7 billion years. If correct, this would provide ample time for ancient galaxies to evolve naturally without requiring changes to the laws of physics themselves. So is the universe truly as young as we believe? Or is everything we know merely a simplified, stretched, and blurred version of a deeper reality? When our best models can no longer simulate what we observe, perhaps the models themselves need to be rewritten. James Webb isn't just illuminating the distant cosmos. It is revealing cracks in the very foundation of the trust modern science has placed in cosmology for over a century. While debates continue around improved galaxy formation models and the potential restructuring of our cosmic framework, another discovery from James Webb has left scientists cornered with no room to look away. Supermassive black holes, appearing too early, growing too fast, and reaching masses far beyond what should be possible within the current age of the universe. One of the most stunning revelations came from the galaxy GNZ11, located just a few 100 million years after the Big Bang. Spectral data suggest the existence of a supermassive black hole weighing hundreds of millions, perhaps even billions of times the mass of our Sun. Standard physics has no explanation for this. A black hole of such enormity shouldn't exist that early. It simply doesn't have enough time. In classical models, black holes are born from the death of massive stars. After collapsing, they slowly accumulate matter over hundreds of millions of years. Even under the most optimistic growth scenarios, the maximum rate at which matter can fall in before radiation pressure pushes it away, a black hole cannot reach 1 billion solar masses within just 300 to 400 million years. So, how did these invisible giants come to exist so soon? One increasingly supported hypothesis is the direct collapse mechanism, in which a primordial hydrogen gas cloud under highly specific conditions no metals, no fragmentation, and immersed in intense gravitational fields, skips star formation entirely and collapses straight into a massive black hole. Recent simulations published by teams at Kyoto University and Harvard suggest this is entirely feasible, provided the temperature remains high enough and cooling is suppressed to prevent the gas cloud from breaking apart into smaller stars. But that's only the beginning. Even if such a rapid formation is accepted, there remains a theoretical wall that has yet to be breached, the Eddington limit. According to theory, black holes cannot grow indefinitely. At high accretion rates, the radiation emitted by falling matter creates a pressure strong enough to repel incoming material, halting growth. And yet, James Webb has observed black holes in the early universe not only growing rapidly, but doing so consistently beyond the Eddington limit for hundreds of millions of years. This suggests that in the conditions of the early cosmos, the very nature of matter, energy density, or even gravity itself may have behaved fundamentally differently from what we see today. Some theoretical physicists now propose that alternate gravitational phases may have existed, where limits like Eddington's were only temporary expressions of physical law, not universal constants. Could black holes have been the first structures to emerge, not the byproduct of galactic evolution, But the original gravitational anchors around which galaxies were built? In the black hole seeding model, the role of black holes is flipped. Not the end of cosmic growth, but the beginning. The blueprint of the universe may have been drawn not by light, but by darkness. If true, what we call black holes may not be the collapse of structure, but the seeds of it. The earliest links in a cosmic chain that shape the architecture of galaxies as we know them. And when the very foundations of matter, time, and gravity are reimagined, the question is no longer how did the universe begin, but rather what object sat at the center of its unfolding evolution? And perhaps it wasn't the light that shaped the universe's path, but the darkness that held it all together. The rapid chemical aging of ancient galaxies doesn't just threaten our current models of stellar evolution. It poses a direct challenge to the very foundation of the Big Bang Theory itself. But in light of the growing tensions between old frameworks and new discoveries, is there anything that still holds consistent between them? The most compelling piece of evidence continuing to support the Big Bang model is the cosmic microwave background. The thermal afterglow from the moment the universe cooled enough for protons and electrons to combine into atoms. This marked the transition when matter became transparent to light. The CMB has been measured with extraordinary precision by missions like COBE, WMAP, and most notably ESA's Planck spacecraft. The data strongly supports the notion that the universe began in a hot, dense state. Another key signature is the cosmic redshift, the phenomenon where light from distant galaxies is stretched toward the red end of the spectrum. This effect aligns with the idea of an expanding universe. Observations from Hubble and more recently James Webb continue to confirm this trend. Every distant galaxy shows redshifted light, suggesting that space itself is expanding over time. But a deeper question emerges. Is redshift definitive proof of expansion, or could there be alternative explanations? A few long-dismissed theories from the 20th century are quietly resurfacing. Among them is the tired light hypothesis, which proposes that light gradually loses energy as it travels through space, producing a reddening effect without requiring cosmic expansion. Intriguingly, cyclical models, such as the oscillating universe or the concept of cosmic rebirth, also recreate features similar to the Big Bang, but without relying on a singular origin point. So if the classical evidence still holds, but can now be interpreted through multiple frameworks, what becomes the deciding factor in determining the truth? Are we placing too much faith in a single explanation when the cosmos may be inviting us to broaden our understanding? James Webb does not disprove the Big Bang, but it does illuminate a parallel path. Where once abandoned models are being given a second chance to prove their validity. And in this intersection between two diverging roads, science now stands at a crossroads, forced to choose between loyalty to the past and the evolution of understanding. As alternative models begin to be seriously considered, a critical question arises. Do we truly have the tools to test them? Or are the limitations of current technology causing us to misread reality itself? James Webb represents a leap forward in our ability to observe the universe, but to truly understand what it's showing us, we need more than a telescope. We need simulations deep and flexible enough to recreate the universe as it actually is, not just as our theories predict. Today's leading large-scale simulations, Illustris, Camel's, Eagle, and Fire 2, are all built upon the standard foundations of physics. Gravity, spatial expansion, and interactions between normal matter, and dark energy. Yet not a single one of these models, even in their most updated forms, has been able to produce galaxies with the size, mass, and maturity that James Webb is observing just a few 100 million years after the Big Bang. The problem isn't just theoretical, it's also computational, bound by the resolution of our simulations and our fundamental ignorance of what dark matter truly is. No one knows its exact nature, and yet nearly all simulations assume it behaves in a cold, smooth distribution, interacting only through gravity. If that assumption is wrong, then the entire simulated structure of our cosmos could be misleading. On the observational side, technologies like gravitational lensing, where massive galaxy clusters bend light from even more distant objects, allow us to peer deeper into the early universe. But without precise calibration, lensing can also distort what we see, exaggerating size, brightness, and even the inferred age of galaxies. The data from James Webb is not based on a single glance. It is the result of hundreds of repeated observations across multiple infrared wavelengths, filtering out statistical noise. What emerges from that clarity? Those massive galaxies, those early supermassive black holes, those anomalous chemical spectra? Are not illusions caused by telescopes or errors in simulation. They are real, and they are challenging the very foundations of modern cosmology. Perhaps what we need now is a new generation of models where data takes precedence and theory follows rather than the other way around. When the map no longer matches the terrain, do we adjust the map or pretend the terrain must be wrong? James Webb is not just watching the universe, it is knocking on the door of the simulation lab, demanding that both theoretical science and computational technology adapt. Or be left behind by a cosmos that no longer fits the blueprint. James Webb hasn't shattered the laws of physics, but it's compelling the entire scientific community to step into a new era, where evolving our understanding is no longer a luxury. It's a matter of survival. The question is no longer whether the Big Bang Theory is right or wrong. The question is, does our current map of understanding still have the resolution to describe the new terrain that James Webb is unveiling? The old models still hold value within certain bounds, but they are no longer complete. They're like ancient world maps, richly detailed in the center but fading into blank spaces at the edges, filled only with speculation. What James Webb delivers is not just information. It's a sense of scientific disorientation, a shock that forces long-standing assumptions to be re-examined. Galaxies forming too early, black holes growing faster than permitted, heavy elements showing up before there was time to make them. Cosmic structures that appear asymmetrical. These things don't fit the old map. What makes science great is not that it's always right, but that it's always willing to be challenged. Progress doesn't come from clinging to theory, but from the courage to confront the data. James Webb doesn't walk this path alone. It is humanity's most distant, outstretched hand. But behind it stand thousands of scientists, engineers, and theorists, opening one door after another. This is not a crisis. It's the return of wonder, the very feeling that first made humanity look up and ask, "What is the universe?" Perhaps what's most unsettling is not that we were wrong, but that we believed we were right so easily. And if galaxies formed before they were allowed to, if time itself doesn't flow as we thought, then maybe it is we, humankind, who arrived late, standing at the edge of the universe, only now realizing that the map we carry no longer matches the world before our eyes. The journey has just begun, and ahead of us, every question is still open. Thank you for staying with WUFO Space until the very end of this journey through the vast universe. If you found this video interesting and insightful, Don't forget to like, share, and subscribe to WUFO Space so you won't miss our next cosmic adventures. Your support means the world to us and fuels our passion to keep exploring the wonders beyond.